Welcome, Greenbrier students, to this screencast when we'll be discussing graphing linear functions. Now, before we get started, we're going to discuss some background information that we're going to need to know going into this. One, we can represent linear functions using a linear equation. Typically, you'll see a linear function in this form, especially when we go to graph it, y equals mx plus b. Now, this is called slope-intercept form. Now, the reason it's called slope-intercept form is two pretty obvious reasons once you define some of these variables. Y represents your output, x represents your input or your domain, here x, y being the range, but m represents your rate of change. Okay, we're going to talk a lot about rate of change in class, i.e. the slope. So again, one part of the slope-intercept form, there's the slope. B represents your y-intercept. Okay, so this is where your function, your linear function, and this linear equation, when we graph it, this is where it intersects the y-axis. Okay, now just real quick, you also have standard form. I'm going to write it down here in green. We will discuss this. Ax plus by equals c. This is called standard form. I want you to be familiar with it. We'll talk about converting from this standard form to slope-intercept so that we can graph using some algebraic manipulation, okay? And keep in mind some of the vocabulary we went over in the last video. You're going to need to keep in mind terms like domain. All right, you're going to need to keep in mind terms like range, keeping in mind that the domain, those are your inputs, the range, those are the outputs of this linear function. And we're also going to talk about an input-output table, which typically we will write it as an x, y table, okay, or using the two variables that are involved in our equation. X is representing our input, y's representing our output. So that's some background info that we're going to need to know going into graphing these linear equations. So let's take a look here at one. Here's one written in that slope-intercept form, y equals mx plus b. Y equals negative 1/5 x minus 1 here. Well, here's your slope, okay, or rate of change, and this minus 1 or negative 1, that's going to be our y-intercept. So that kind of helps us visualize what this will look like. But what I want us to do, all right, and this is negative 1 is our y-intercept. What I want us to do is create an input-output table to graph this linear function. So let's write x, that will represent our inputs, y representing our outputs. And what I recommend you do is, because you have this fraction 1/5, use numbers, okay, use numbers that are evenly divisible by 5. And all we need, okay, are 3 points. Really, you just need 2 points to define a line, but I'm going to encourage you to use 3 to help us be a bit more precise. So I'm going to use 3 numbers that I know fit on this x-axis that are divisible by 5. What I'm going to use is negative 5, 0, okay, 0 divided by 5 is just 0, so I can use that, and then positive 5. Now I'm going to input these values into this function and see what my output is. So for instance, negative 1/5 times negative 5 minus 1. Well, negative 1/5 times negative 5, that's 1. Now minus 1, that's 0. When I input negative 5, my output is 0. Now I'm going to try that for 0. Negative 1/5 times 0 minus, so that's minus 1, equals 0 minus 1, because negative 1/5 times 0 is 0, and that gives me negative 1. Now, a third time, negative 1/5 times 5 minus 1, that equals, well, negative 1/5 times 5, that's negative 1 minus 1, and that's negative 2. So now let me plot these points. I'm going to plot them in red. Negative 5 is my input value, so move to negative 5 on the x-axis, and my output value, my y, is 0. So there's negative 5, 0. And notice, these are ordered pairs, right? So negative 5, 0, all right, 0, comma, negative 1 here, and 5, comma, negative 2. So these are, all right, a part of the solution set for this linear function here, for this linear equation. So let me rewrite this one. There we go. 0, negative 1, not going to move anywhere on the x, move down 1 on the y, and then move over to the right 5, down 2, and now you see these 3 points are collinear. They lie on the same line, and so therefore I'm going to draw a line through these points, and I'm going to start here and drag it through them, and I'm going to adjust that line just a little. See if it'll let me do that. There we go, got that line adjusted, and now you see we've graphed this linear function. Okay, so we've got a linear equation here representing a linear function. We created an input-output table, and then we graphed it. Notice it has a negative slope, negative 1/5, and therefore as we read from left to right, this is sloping downward. Okay, so it's key to look at these functions as they're graphed and interpret some of the characteristics. Now go ahead and pause the video and try number 2 here on your own. Create an input-output table using 3 inputs, resulting in 3 outputs, and then graph it on a coordinate plane much like this one. All right, hopefully you've had a few moments to create your input-output table for this function. I just used one negative number, negative 1. I used 0. Often it's important to use 0 as an input value. That tells us where we're going to cross the y-axis. Notice we cross the y-axis at our y-intercept. And here, notice there's an understood 1 in front of x, so our slope is 1, y-intercept's negative 3. If you remembered over here, all right, slope was negative 1/5, y-intercept negative 1. You can see that there. So I created an input-output table. Negative 1 resulted in negative 4 when I substituted negative 1 into my linear equation representing my linear function. I substituted 0 into the linear equation and got negative 3 as my result. And then when I substituted 1, I therefore got the range value, the output value, negative 2. When I graphed them, here I have them graphed in purple, I then drew an orange line. Notice the arrows on both ends. These functions go on forever and ever, so it's important to go ahead and use correct notation and correct illustrations. Put arrows at the end of your linear functions when you graph them. So this line, all right, represents our input-output table, which represents this linear equation, which represents a linear function where x is our independent variable, our input, our domain, and our y is our dependent variable, okay, our output or our range. Now, here's another one real quick that I want to look at. How about x equals 4? Notice this isn't a y equals, okay? This is just x equals 4. Well, think about it. No matter what we do, okay, our input value is fixed. X is always equal to 4. I can't choose my input value in this case. X has to equal 4. But x equals 4, notice, has no bearing on y. Meaning, x equals 4 and y can equal negative 1. X equals 4, y could equal 1. X equals 4, y could equal 0. X equals 4, y could equal, I don't know, 6. Notice, my input value is fixed, but my output value is not affected by the input. This is not a function, if you notice. Notice this domain is associated with multiple range values. And it would look something like this. All right, 4, -1, 4, 1, 4, 0, and 4, 6. Notice this input-output table represents a set of ordered pairs. I can now graph this, and I think if you take a moment to think about it, these lines, they're collinear. These points, are collinear, and they form a vertical line. This vertical line is not a function. All right, so I want us to be very careful. This is not a function, and we'll talk about that in another video. But this is not a function. There's a simple test called the vertical line test that would show us this graphically. But then we can also just look at our input-output table. I use 4 inputs here. It's fixed at 4. And notice multiple outputs. I could pick any output for this input, and 4 is associated with a ton of outputs, in fact infinitely many, and this creates a vertical line which is not a function. All right, these two are functions. Each input's associated with one output, each domain value associated with one range value. This is not the case. It is not a function. This, when you have x equals a number, forms a vertical line, and that is not a function. All right, that's it for this screencast. I'll see you later, students.